Hello everyone, my name is Ashutosh Raut and today I am going to explain you what Raman effect is and some theories that is connected to Raman effect. Okay, so let's start. Let's start with the definition of Raman effect. Okay, when a monochromatic radiation scatters from a matter, the large part of the scattering radiation have the same frequency as the incident radiation, but in addition we get two types of radiation lines in which one type has a less frequency than the incident radiation and the other type has the more frequency than the incident radiation. Okay, this is how I can do it in simple way. Okay, अगर हिंदी में बोलना हो तो जब जब एक वर्णी प्रकाश का स्रोत है वहां से प्रकाश आता है किसी मैटर पे गिरता है वहां से उसकी स्कैटरिंग होती है मतलब स्कैटरिंग को हिंदी में क्या बोलते नहीं पता बट जैसे तितर बितर होना या ऐसा अपन बोल सकते हैं ठीक है तो जब उसकी स्कैटरिंग होती है वहां से तो अपने को जितना स्कैटरिंग वाली जो ये प्राप्त होती है जो रेडिएशन प्राप्त होती है उसका लगभग 95 to 99% जो हिस्सा होता है वो होता है उसकी फ्रीक्वेंसी उतनी होती है जितनी आने वाली जो प्रकाश की रेडिएशन थी उसकी जितनी आवृत्ति होती है ना उतनी ही आवृत्ति स्कैटरिंग वाले रेडिएशन की भी आवृत्ति उतनी ही थी बट एडिशन में अपने को दो छोटी छोटी लाइनों के अपने को बैंड्स मिलते हैं छोटी छोटी लाइनों के बैंड्स मिलते हैं जिसमें से एक में जो फ्रीक्वेंसी होती है वो कम होती है जो आवृत्ति होती है वो इंसिडेंट वाली आवृत्ति से कम होती है और दूसरे में अधिक होती है ठीक है दिस इज नोन एज द रामन इफेक्ट ओके एंड रमन discovered this in 1928 and on his name this effect was known as the Raman effect. Oh, this was a really big phenomena. It was some kind of a miracle and he got a Nobel Prize for it. But there was a problem how this is happening. There was no explanation at that time. Okay, let me just tell you the Raman effect again by some animations. Look at this. This is a matter. This is the incident radiation falling on it. Okay, and it has a frequency. Let me just do it in a big way. This is pen. I think it has to be okay. Okay, so this is the radiation. Okay, this is red, so you won't be able to see. Okay, let me make this white. Okay, erase it. Now look at this. This is the incident radiation falling on a matter and it is getting scattered from that and it has this is the scattered radiation and it has the same frequency as the incident radiation. Okay, frequency is denoted by nu here and incident so we took the I from the incident, so incident radiation frequency is Vi denoted by Vi. Okay, and the scattered radiation's frequency is denoted by mu-ness. Okay, this is not V. I mispronounced it. This is pronounced as mu. It's one of the Greek letters. Okay, no, Latin letters. There is a whole alphabet series of alpha, beta, gamma, delta. Okay, this is one of those. Okay, so this is the incident frequency is denoted as nu I and the scatter frequency is denoted as nu S. Okay, so when let me just explain you in here. When nu I is equal to nu S, then it is which means the scattered radiation has the same frequency as the incident radiation. This is known as relay lines. Okay, and that is just a name given to it. Okay, the relay lines was discovered way before than Raman, so the person who did it, that was the lines were named after him. Okay, so relay is the person who did it. So when this is as this is the spelling of his name. Okay, this is relay lines. Okay, but when the incident frequency is smaller than the scattered frequency, then it is known as anti-Stokes lines. Anti-Stokes lines. Okay, and when the incident frequency is bigger, more than the scattered frequency, this is known as Stokes lines. Stokes lines. These are just names these are just name given to it. Okay, do not pay any much attention to it. These are just names that has been given to it. Okay, so just remember, when the frequency is less, it is stroke lines. When the frequency is higher, it is anti-stroke line. When the frequency is same as the incident frequency, it is relay line. Okay. Now let's move on to this. This is a animation and display. Let me just show you here. Okay, this is the incident radiation. This is the scattered radiation. When mu I incident radiation frequency is equal to scattered radiation frequency, this is known as relay lines. And when the frequency of the scattered radiation is less, it is known as stroke lines. When the frequency of the scattered radiation is higher, it is known as anti-stroke lines. Okay, I had explained you this before, and these are just definition that I have written here. If you want to take this, just take a screenshot. Okay. Now let's move on to the Raman shift. Okay, like I had explained you before, this like this. Look, like I have told you before, the shift what I told you before. I have told you before about stroke and anti-stroke lines, right? So nu I is the incident frequency. Let me make it a little bit bigger. So this is the incident radiation frequency. This is the scattered radiation frequency. When we take the difference of these two frequency, it is denoted as delta nu, and this delta nu is a term which is been referred as the Raman shift. Okay, so the difference in the frequency is known as Raman shift. Okay. So, like I have told you before, in stroke lines, this frequency is less than red scattered frequency is less than the incident frequency. So, which means this term will be positive. So you can write it as when the Raman shift is positive. When the Raman shift has a value positive, then then it's a stroke line. Okay, and if this value is bigger than this value, then this value will be like negative, right? So when Raman shift is negative, these are anti-stroke lines, and when they both are equal to each other, this will be 0. So that is relay line. Okay, understood? Now let's move on. Okay. Now we are going to talk about the quantum theory. Okay, before we go to quantum theory, let me just explain just a little review from my classmates' presentation. Look, classical theory states that like I have told you that classical theory treats radiation as a wave. Okay, so radiation as a wave, as an electromagnetic wave. So it has an electric field and also a magnetic field connected with it. Okay, the matter had molecules. Matter had molecules, and the electric wave just falls on it. So in the molecule there are atoms, and atoms also have nuclei on electron. Okay, so the nuclei of the atom get attracted to the positive pole of the electric field, and the electrons of the atom get attracted to the negative pole of the electric field. So what does this create? This creates a dipole. Look at this. This is the nucleus and this is the electron. They are getting attracted to two different ways. Like this is the positive pole of the electric field, this is the negative pole of the electric field, and they are getting attracted to them. So it creates a dipole, and dipole also oscillate with the same frequency as the incident radiation has. Okay, understood? This we just denote this frequency as V. Okay, and now just say that this molecule was vibrating already before the electromagnetic radiation hit it. So it also has its own vibration. Okay, and when it also had its own vibration, the Raman shift will occur if it has a vibration. Okay, let me just explain. This is the molecule. It is vibrating like this, and if this is vibrating, the polarizability of the molecule will change. And when the polarizability of the molecule will change, like just say that this was the molecule, it has a positive and negative here, and it is vibrating, so it is going up and it is going down like this, oscillating like this, then the polarizability will change now. Like if this goes a little bit up, then the positive pole will get attracted by the nucleus will get attracted by the negative pole little bit harder, and this will go like little less than the previous one. So the polarizability will change, and when the polarizability will change, the Raman effect occurs. Okay, so this is the classical theory. It also has a derivation, and the electric field is defined as E sine 2 pi nu t, E naught sine 2 pi nu t. This is the derivation of the this is the formula of electromagnetic field. Okay, the strength of the electromagnetic field, and this frequency is the frequency of the electromagnetic wave, and as well as the frequency of the oscillation of the uh, dipole. Okay, the magnetic dipole. Okay, and now the magnetic dipole also has a formula like nu is equals to alpha into E. Okay, this alpha is a polarizability. Okay, and this alpha is defined as A naught plus beta into x by A. Okay, what is this x? This x is the displacement. Like this is the molecule, it is oscillating, I mean vibrating, and this just travels this distance from its equilibrium position, that is denoted as x. And look, this is oscillating like this and like this. So what does it look like? It looks like a linear harmonic oscillator. Okay, and linear harmonic oscillator has a formula of the displacement as like this. 2 pi, okay, let me just clear this one, as x is equals to a into sine 2 pi nu. This is the frequency of the oscillation. This one is the frequency of vibration, sorry, oscillation frequency this. So we will put this value in the alpha, and we will get like alpha naught plus plus beta into sine 2 pi nu v into t, and E is denoted as E is equals to, sorry, the nu is denoted as nu is equal to E alpha into E naught sine 2 pi nu into t. So we will just substitute this value here, and we will get some terms in which it is a really long derivation, but let me just tell you that this will get multiplied with this separately, and this will multiply with this separately, and we will have a formula like this. We will apply the sine v into sine v is equals to cos a minus b and minus cos a plus b. Okay, if you are watching this video, you are graduated. Oh yeah, sorry. Okay, we can we can just transmit this to here from here like this. Okay, we can just remove it. Just consider it removed. Okay, now even if you are watching this video, you are already graduated, so you know how to substitute values and get this, and we will get a big term here. Okay, this is the term nu is equals to this alpha E naught sine 2 pi mu t plus 1 by 2 beta E naught cos 2 pi nu minus nu vibration into t minus cos 2 pi nu plus nu vibration into t. This is the formula for the classical theory. Okay, and these two terms are for here for Raman effect, and this one here is for the Rayleigh lines. Okay, this was the classical theory. And now we will move on. Now we will move on to the quantum theory. Quantum theory treats light radiation as a electromagnetic, no, not as a electromagnetic, as a photon also. Okay. Photon is a particle having energy h nu, having energy h, having energy h nu. This is the energy of the photon. Okay, and in this quantum theory, we will just use a diagram. Let me just go to the diagram. Okay, look at this. Okay, so just say that you already know that the molecules vibrate, and they also have their vibration energy state and rotation energy state, right? And when you give molecules energy, they jump from one energy state to lower energy state to higher energy state, and they cannot stay there for a long, so they just come back to their original state. Okay, so we have studied this in the vibration spectra and rotation spectra. Let's talk about this is the lower energy state, this is the little higher energy state, and this is a virtual state which could be higher. You can imagine how it depends on your imagination how high you want to put. Okay, so now there is a photon, like I have told you. We treat light as a photon. Okay, so this photon has an energy h nu, and this photon just falls on this molecule. The molecule absorbs its energy. It goes to the higher state. It cannot stay there for a long, so he comes back to his original position and emits photon back. This is known as a relay set, relay lines, because the molecules emit the same energy that it absorbed before. Okay, in the other, there is a molecule, it absorbs the energy, it goes to the higher energy level, and it does not come back to its original energy level. It stops at a little bit higher, so it has taken some energy from the photon. So now the scattered photon will have a less energy, and this is when the scattered photon has a less energy, which means the wave has a less frequency, and this is known as the Stokes lines. And in the same manner, if some molecule was already in this state, okay, this is his ground state, and he absorbs energy, it goes to the higher level, and he comes back, but he does not stop at his original state, he goes a little bit lower. So the molecule emits bigger energy than it absorbs, so the photon will have a bigger energy, and which means the wave will have higher frequency. Okay, so this is for the anti-stroke lines. Let me just show you how this works. Look at this. For the Stokes types, this is the, sorry, why isn't it working? Okay, look at this. This is the incident. Energy of the photon. As I have told you that there is a molecule and there is a photon. Photon gives energy to molecule. Molecule goes to the higher state. It comes back, but not on the state that it should. It come back to the little bit higher state, which means it has absorbed energy from the incident radiation. So this was the energy of the incident radiation. Let me make it a little bit bigger. Look at this. This is the energy of the incident radiation, and this amount of energy has been taken by a molecule, so he could stay in the higher energy level, and this is the energy of the this is the energy of the scattering radiation, right? So which means this energy is less than this energy by amount of this del nu. So this is how we define Stokes lines. Okay, and if you want to calculate the frequency, you can just divide by h, and you will get the frequency also. This was for the Stokes, and we can do that for the anti-stroke too. Look at this. The anti-stroke in the anti-stroke. Okay, sorry. In the anti-stroke, the incident radiation has this amount of energy, and this was the energy that was given to the radiation by molecule. So we add them and we get the radiation of the scattered radiation. Scattered radiation. We get the energy of the scattered radiation. Okay, which means this value will be bigger than this value. So by amount of this is known as Stoke lines, anti-Stoke lines, sorry. And if you just want to calculate the frequency, we can just divide by h and we will get this. So this was the explanation of the Raman effect, quantum theory of Raman effect, and classical theory of Raman effect. Okay, thank you. Okay, so I have just explained everything, but we just missed one thing, which was the intensity of lines. Okay, this is the graph. Sorry, white pen. Okay. This is the graph of the intensity. This is the axis of intensity. Intensity. And this is the axis of frequency. Okay, this is okay. Now then, the Stoke lines have frequency of this amount. The Stoke lines have intensity of this amount, and the frequency of the Stoke lines is less than relay lines and anti-Stoke lines, right? And anti-Stoke lines, sorry, the relay lines have the frequency in the middle of Stoke and anti-Stoke, like this. Look, this is intensity of relay line. Sorry, this is the intensity of relay line. This is the intensity of Stoke lines, and this is the intensity of anti-Stoke lines. Frequency is increasing in this axis. So Stoke line have less frequency. Relay line has a little bit higher, and most highest is anti-Stoke lines. Okay, but this is for the intensity. So relay line has the most intensity, and then Stoke lines have intensity, and then anti-Stoke lines. There, in according to classical ways, they both line, they Stoke and anti-Stoke should have the same frequency, but in experimentally we have found that Stoke lines have more intensity than anti-Stoke lines, and quantum theory explains this as like probability. Okay, the Stoke lines have higher probability than the anti-Stoke lines of appearing. Okay, let me just explain this with a mu. Okay, uh, in in uh, in quantum mechanics, we define it as like this: nu sin beta. This nu is also equal to, it also has the same value. Okay, but we just denoted in a different way, like this, like alpha naught plus beta x by a, and we'll just denote this as it is. So we will just put this value in here, and what we will get? We will get like this, sin naught alpha naught into e, and psi. This is m, this is n. Okay, m and n and d tau plus plus this value. The beta and a are also constant, as as a is constant, and as also e is also constant, because electromagnetic wave have the same strength everywhere. Now this x is changing because the molecule is vibrating, so x is the only thing that is changing. So we just put it into here like this. This is the also the quantum derivation, or the quantum theory's derivation for the probability of finding. Okay, thank you.